Hello everyone. In this particular video, we are going to see right address channel. This is the most important one as we will be covering lot of concepts in this single channel. Previously what we have seen the case scenario of AXI, why we needed AXI. Then we have seen what exactly is AXI, what are the characteristics of AXI, what is this protocol actually is. Then we have seen the AXI channel architecture, how many channels are there, which channel do what. Then we have seen the signals included in all the channels. Then next we have seen the handshaking in AXI, how handshaking happens, what exactly handshaking means, what are the constraints in handshaking, how we can delay the transaction using the ready signal. The delay in ready signal will delay the transaction. This all is being covered. Now we will be starting with this right address channel. If you need any other explanation regarding whatever we have learned till now, or you have any doubts, you can drop a comment. Before moving to this video, I better ask you to go through all the previous videos whatever we have covered, so that you can have a proper understanding of this particular video, because to understand right address channel, all previous videos are mandatory. So in our right address channel, what are the signals we have? I have taken them over here. At first we are having handshaking signals. How these handshaking signals are used, we have covered it in our previous handshaking video. Go and watch that. Next, this is the main signal which is of use over here using this right address channel. This is the address which we will be transferring. Other signals, all these other signals are control signals. Out of these control signals, some of the control signals which we will be learning and which are of use for us to get the concepts cleared. So is this AW address means the starting address of right transaction. So we are having a memory. When we say starting address, this memory is divided like this. We want to start the write from over here, then this, then this, then this, and in this memory. So what we do is we provide this starting address. Let us say it is 0x1000. So we'll provide this starting address to this right address signal that we want to start the write from over here. Next we are having AWID. This is a unique ID assigned to each transaction so that we can identify which transaction is what. Before explaining you next these signals, let me explain you these three concepts. What is a beat, what is a burst, and what is a transaction. There is one master, there is one slave. From master to slave, the data is being transferred in some of the data chunks. So this is one individual data chunk, this is individual, this is so one of like this. There are 6 data chunks required to transfer this data from master to slave. So this was the complete data. We have break down it in different chunks. This one chunk was delivered like this. So this single data value, data unit, is called beat, which is transferred from master to slave. Then the collection of all the beats, we say this is a burst, the whole group of beats. Now in AXI, we know we have write 3 channels. If you haven't watched the architecture of AXI video, prefer watch that video so that you can understand what I will be explaining regarding these channels. So from master to slave, we have sent the data, the address like this. It is address being sent. Then the W data, that is the actual data, is being sent to slave. Then after this data is written, slave is sending one response that your data is being written. So this whole, the sending of address, the sending of data, and the receiving of response, this whole is a single transaction. So that means transaction says from request to response, this whole complete process is known as one transaction. Now let us get back to the signal explanation. So over here in these signals, AWID is the unique ID for each transaction. That means whenever we are sending this data transaction from here, the address, the write data and the response, among these three channels, this AWID will be unique for each transaction. This is actually used to check which response of transaction we have received. You might be sending lot of transactions together. Some might be processed earlier, some might be later on. So using this response, this ID, you will get to know for which transaction you have received the response in master. Next we are having AW length. This is actually we call burst length, or you can simply say this is the number of bits in which data will be transferred. This is of 8 bits. That means it can contain value from 0 to 255. Then we are having AW size. This is the data size of each bit. How much data each beat will be containing. It is of 3 bits. This value ranges from 0 to 7, but the bytes transferred in each bit, we calculate it how is 2 to the power of AW size. That means when this value is 0, 2 to the power 0, so when we have set it this AW size as 000, so the actual data transferred per bit will be 1 byte. I'll be explaining you further with the table also this. Then we have the AW burst, the burst type. How your address will be incrementing, because you have only given the starting address. Now how the protocol will be moving to next addresses, this we give in burst type, AW burst signal. Then these are some of other signals which are not of much greater concern, but these signals which we have explained I have explained to you are of much interest. Then we are having this signal description over here. In signal description, the very first signal is AW length, that is our burst length. So in burst length, we know it is of 8 bits. If the initial value is 00000, so that means it is 0, so the number of bits will be 1. If it is 0001, that means the number of bits will be 2. So how, if it is 0, that means 1 bit, so from master to slave, the data will be transferred in a single beat like this. This is data. If 2-bit burst is there, then from master to slave, how data will be transferred in 2 bits like this. This is 1, this is 2. This whole will make data. This is beat 1, this is beat 2. So simply, if AWLN is 010, that means 2 in binary, that means 3 number of bits. So how from master to slave, how data will be transferred? 1 data, 2 data and 3 data. In 3 bits it is being transferred. Next we are having AW size, that is we call burst size or data contained by each bit. So if it is 0, it is of 8 bit 3 bits, that means it can vary from 000 to 1111. So if it is 0, how many bytes per bit will be transferred? 2 to the power 0, that is 1. If it is 1, 2 to the power 1, that is 2. If it is 3, if it is 2, 2 to the power 2, that means 4 bits transferred per bit. So I hope you are clear with this. from master to slave if we are sending data in beats, and if this particular beat is containing, let us say, the AW size we have fixed this 001, that means bytes per bit will be means 2 bits of data, 2 bytes of data, then 2 bytes of data here and 2 bytes of data here. So total data transferred is 6 bytes. So this table will be very helpful for you to understand how much data is being transferred from master to slave. Let us say at first we are having AW length 0. When AW length is 0, that means number of bits will be 1. So in single bit the data will be transferred. And AW size we have fixed as 2, that means 4 bytes of data per bit, so that means 4 bytes. So total data transferred is 4 bytes. In next case, what it is there, number of bits is 2, that means 2 bits. AW size is fixed, that is 4, that means 4 bytes of data each bit. Total data transferred is 8 bytes, right? So using AW length and AW size, we can manage how much data will be transferred in one transaction, or you can simply say in one burst, because this group of bits will become burst. Then we have the AW burst size. So when we say AW burst, we are having 4 values as it is of 2 bits, 00, 01, 10, 11. This 11 is reserved as of now. When it is 00, that means burst type is fixed. That means a fixed address will be sent for all the bits. Where it is being used, we have some of the FIFOs from where data is being utilized further, and the address of this FIFO is fixed. This we call as FIFO address. So all data will send to this single address, and it will keep on going internally in the FIFO, and it will be used. So this is a fixed address type in AXI supports. Then we have INCR. This is the most common basic one which we use. If we have a memory and we give this starting address as, let us say, 0x1000, and we are transferring 2 bytes of data per bit, then the next address will be 1002, then 1004, then 1006, then 1008. So that means the address is incrementing. So this is used, this INCR address increment is being used in sequential memory block like RAM's DMA. So this is how the memory is being accessed. We only provide the starting address to AXI. Next addresses are being calculated by AXI automatically. Next we are having wrap address. So in wrap address, what happens is we have one starting address and we have one boundary address, that our address can't go far beyond this address. So once it reaches the maximum address, it routes back to the initial address. Why it is required? Let us say we have a circular buffer like this. These are circular buffers, and the address of this is 1000, and the address of this is 1008. So what happens is the address will increment in each bit, and once it comes to 1008, it will reset to 1000. So this is where the wrap address is being used. So these are 3 types of burst types which you can provide in AXI: fixed, increment, and wrap type. Let us see working of one write address channel of AXI. We have taken demo values over here. The address we have fixed, starting address we have given as 100, then AWID we have given as 5, the burst length we have given as 0011, that means 3. So that actually means is 4 number of bits will be transferred. That means 4 bits per burst transfer will be there. Then we have the AW size 010, that is 2 in binary. That means number of bytes transferred in each bit will be 2 to the power AW size, that is 2 to the power 4 is equal to 4 bytes per bit. Then AW burst type we have set it as 01, that is 1. That means burst type is INCR. If you see this, if it is 01, the burst type will be INCR. So INCR we have set it. The address will increment by 4 because you see 4 bytes per bit are being getting transferred. So if the address is 1000, then it will move to 1004. So using all these signals, what actually master has configured the slave as, that master has configured it as, I will be sending, master says to slave that I will be sending a transaction with transaction ID 5, as AWID is 5, where starting address will be 0x100. This is the address, starting address, with burst type INCR. Using AW burst we have set it this burst type, where each bit will contain 4 bytes of data. Using AW size we have set it this as 4 bytes per bit, and the transfer will complete in 4 bits burst. So AW length we have set it 4 bits burst transfer it will be. So how actually the transfer happened over here is, in bit 1 the address is 0x100, 0x100, this is the very first bit. Then second bit is 0x1004, then third bit with address 1008, fourth bit will be having address 100C. So you see 4 bytes of data is being transferred per bit, and this single burst is having a transaction ID is 5. It is same. So the total data transferred over here is 4444, that is 16 bytes of data has been transferred over here, right? So this write address channel was important one because we have covered lot of concepts in this single write address channel. So if you understood this one, other channels are very easy for you to understand. Next we will be moving to write data channel. In write data channel we are having two signals, W valid, W ready. These are handshaking signals. If you haven't watched the handshaking video till now, go watch that so that you can have a very clear understanding of these two signals. Then we are having write data. This is the actual data in which we are interested. This data is to be written. The master will be sending this data to slave to write this data. This W last is a signal which explains that this is the last data which master is sending. This W strobe and W user are other control signals. So master will transfer the W data to slave once handshaking is done based on the specifications set it in write address channel, because over there we have set it the bit, the burst type, the burst length, all. So this data will be transferred based on the specifications set it in the write address channel. Then we are having one write response channel. In write response channel what we are having is these two again handshaking signals. Then we are having this B response signal which is of our interest. B ID is also of our interest. B user, these are other control signals. This is the main signal B response in which we are interested. So what happens is, in this case slave will become the source because it is going to send the response signal, and master will become the destination. So as I have explained you in the previous video, this time slave has become the source and master has become the destination. So how handshaking will be done over here? Slave will send the valid signal that I am having a valid response. Master will send a ready signal that I am ready to receive the response. This has been explained previously in very detail. So once handshaking is done, this B response is being sent by slave to master. So there are different, this slave B response is of 2 bits wide. It is 2 bits wide. So what it sends is 00011011. So when it says 00, that means you write whatever you have written in the memory, you have sent your data, it is being written in this particular memory. Next we are having a exclusive OK. This I'll explain you now after all this. Then we have slave error. When we receive this responses that slave was unable, this write was not successful. Then we have decode error. That means the address which is being sent by the master is not found in memory, or it is not being mapped to in slave to any memory. So now we'll take this, what actually is this response type exclusive OK. So what it is master wants to, there is one memory, this is slave memory, this is CPU. Now the CPU wants to write to this memory with address 100C or 0x100, and as we know AXI supports simultaneous write and read. This is explained in the first video, characteristics of AXI. So it might be the case that at the same time one channel 1 might want to write to this particular location, and channel 5 want to read this particular location. So there might be a possibility of conflict. So what happens is, when we say we have set our transaction as exclusive transaction, so when we have set it our transaction as exclusive transaction, what happens is, when a transaction is exclusive, master will first read this location. This location is being first read, then it is being written, and until sending this response back, if this the value which master has written is not being changed by any other master, there might be multiple CPUs connected to this memory which might be changing the location. So until and unless if this memory has not been changed, so the response sent will be exclusive OK response, that whatever the memory you have written, it is not being changed by any other master. In case if this particular memory is being changed by any other master, what it will send is, it will send simple OK signal. That means your memory location which your master has written is being inferred by another master. So this is exclusive OK. Moving further ahead, we will be understanding the read channel, the read address channel, and the read data channel, and some other additional concepts, ordered and unordered transactions in AXI, aligned versus unaligned addresses in AXI, outstanding transactions in AXI, though these all will be looking ahead in further videos. So keep learning, keep watching. Thank you all.